Have you ever wondered how your device gets its unique identity on the internet? The answer lies in IPv6, the backbone of internet addressing. Let's take a step back and understand what IPv6 is all about. The internet, as we know it, relies heavily on IP addresses, which are unique identifiers for devices connected to the internet. IPv6, or Internet Protocol version 6, is the most recent version of the Internet Protocol, the communications protocol that provides an identification and location system for computers on networks and routes traffic across the internet. IPv6 was developed by the Internet Engineering Task Force to deal with the long-anticipated problem of IPv4 address exhaustion. You see, IPv4, the predecessor to IPv6, used a 32-bit address scheme which could support around 4 billion unique addresses. As the number of devices connected to the internet exploded, we quickly realized that this was not enough. Enter IPv6. With its 128-bit address scheme, it can support a staggering number of unique addresses. We're talking about 340 undecillion addresses. That's a number so large it's hard to comprehend, but let's just say it's enough to assign an IP address to every atom on the surface of the Earth and still have plenty left over. But IPv6 isn't just about more addresses. It also brings along several improvements over IPv4. It simplifies the address configuration process, improves the routing efficiency, and enhances security and privacy, among others. The structure of an IPv6 address is also different, consisting of 8 groups of 4 hexadecimal digits separated by colons. This structure allows for a vast number of unique addresses, ensuring each device on the internet can have its own identity. As we find ourselves in an increasingly connected world, understanding IPv6 becomes more and more crucial. It's not just about keeping up with the tech jargon. It's about understanding the fundamental building blocks that make our interconnected world possible. With the world moving towards IPv6, it's essential to understand its intricacies to keep up with the evolving internet landscape. Now that we know what IPv6 is, it's time to delve into the practical aspect, configuring and verifying IPv6 addressing and prefixes. Let's start with configuring an IPv6 address. This process is relatively straightforward. First, you need to enter the interface configuration mode. From there, you specify the IPv6 address and the prefix length. The prefix length, denoted by a slash followed by a number, indicates the number of bits in the network portion of the address. For instance, if you have an IPv6 address of 2001 0db8 85A3 0000 0000 8A2E 0370 7334 and a prefix of 64, you would enter the address as 2001 0db8 85A3 0000 0000 8A2E 0370 7334 64ths. This tells the system that the first 64 bits of the address are the network portion, and the remaining bits are for host addresses. Now, let's move on to verifying the IPv6 address. This can be done using the Show IPv6 Interface command. This command will present a detailed summary of the IPv6 address, including the prefix length and the link local address. An essential part of IPv6 is the prefix. The prefix in an IPv6 address serves a similar purpose to the subnet mask in an IPv4 address. It separates the network portion of the address from the host portion. This separation is crucial for routing and network organization. To configure the prefix, you simply include it when setting the IPv6 address, as we discussed earlier. In conclusion, configuring and verifying IPv6 addressing and prefixes isn't as daunting as it might seem at first glance. It's all about understanding the structure of the IPv6 address and the role of the prefix. By getting a firm grasp on these concepts, you'll be well on your way to mastering IPv6. Mastering the configuration and verification of IPv6 addressing and prefixes is a crucial skill for any network engineer. Imagine a world without wireless internet. Hard, right? Thanks to 802.11 wireless, we can seamlessly connect our devices without any wires. But what exactly is this 802.11 wireless? Well, it's a set of standards established by the Institute of Electrical and Electronics Engineers, or IEE, to define how wireless networks operate. Now, let's dive a little deeper. The 802.11 wireless standard is actually a family of specifications, each represented by a letter. You might be familiar with some of them: 802, 11A 802, 11B 802.11G, and 802, 11N. Each of these represents a different generation of wireless technology with varying capabilities in terms of speed, range, and frequency bands used. Let's start with 802, 11A. This standard operates in the 5 GHz frequency band and can support data rates up to 54 megabits per second. Then we have 802, 11B, which operates in the 2.4 GHz band and supports a maximum data rate of 11 megabits per second. Next up is 802.11G, which, like 802, 11B, operates in the 2.4 GHz band but supports a higher data rate of up to 54 megabits per second. And finally, we have 802, 11N, also known as Wi-Fi 4. This standard can operate in both the 2.4 and 5 GHz bands, and it supports data rates up to 600 megabits per second. But the advancements didn't stop there. We now have newer standards like 802, 11AC, also known as Wi-Fi 5, and 802, 11AX, or Wi-Fi 6, which offer even greater speeds and more efficient use of wireless spectrum. So you see, 802.11 wireless is not just about eliminating wires. It's about continually improving the way we connect to the internet, making it faster and more efficient. And with each new standard, we get closer to a future where high-speed, reliable, wireless internet is available to everyone, everywhere. 802.11 wireless has revolutionized the way we connect to the internet, making our lives much more convenient. Wireless communication may seem simple on the surface, but it's underpinned by complex principles and components. Let's take a deep dive into the fascinating world of wireless technology. At the very heart of wireless communication is the principle of signal transmission and reception. This is all about how data is sent from one place to another without the need for wires. Imagine tossing a stone into a pond. The ripples that spread out are very much like the radio waves used in wireless communication, spreading out from the source and being picked up by a receiver. Now, let's talk about the key players, the components. The most critical piece of a wireless system is the access point, or AP. This is essentially the hub of a wireless network, broadcasting the signal that your devices connect to. Think of it like a radio station, sending out your favorite songs for you to pick up on your car radio. Next up, we've got the wireless clients, which are devices like your smartphone, laptop, or smart TV. These are the receivers picking up the signal from the access point and using that connection to access the internet or a local network. It's as if your car radio picked up those songs from the radio station and played them for you. We also have other components such as wireless routers and antennas, which play crucial roles in amplifying signals and directing them to the right places. Think of them as the sound engineers at the radio station, making sure the music reaches your car radio loud and clear. And let's not forget about the protocols like 802.11, which set the rules for how data is transmitted and received. These are like the language that your devices use to communicate with the access point and each other. In conclusion, wireless communication is a symphony of different components and principles working together. A deep understanding of wireless principles and components is fundamental to managing and troubleshooting wireless networks. Ever wondered why Wi-Fi channels don't interfere with each other? The secret lies in non-overlapping channels, but that's not all. Our data needs to be protected too, and that's where encryption comes in. Wi-Fi operates in two frequency bands, the 2.4 GHz and 5 GHz. In each band, there are multiple channels available for use. However, not all channels are created equal. Some of them overlap with each other, which can lead to interference and degraded network performance. To avoid this, we use what's known as non-overlapping channels. In the 2.4 GHz band, there are only 3 non-overlapping channels, 1, 6, and 11. By choosing one of these for your Wi-Fi network, you can ensure that your signal doesn't interfere with those of neighboring networks, providing a smoother, more reliable connection. But what about the 5 GHz band? Well, the good news is that all channels in this band are non-overlapping, offering more options for network configuration and potentially less congestion. But ensuring smooth network operation isn't just about avoiding interference. It's also about protecting the data that's being transmitted. That's where encryption comes in. Encryption is the process of converting data into a code to prevent unauthorized access. When you send data over a Wi-Fi network, anyone within range could potentially intercept it. However, if that data is encrypted, all they would see is a meaningless jumble of characters. There are several encryption standards used in Wi-Fi, including WEP, WPA, and WPA2. Of these, WPA2 is currently the most secure, using a protocol known as AES to provide robust protection for your data. So by carefully selecting non-overlapping channels and implementing robust encryption, we're not just optimizing our wireless network. We're also protecting our data, ensuring that our personal information, business communications, and online transactions remain secure and confidential. By carefully selecting non-overlapping channels and implementing robust encryption, we can optimize our wireless network and protect our data. Let's take a moment to recap the key points we've covered in this video. We started with an introduction to IPv6, the most recent version of the Internet Protocol that is gradually replacing IPv4. Its larger address space is indeed a game changer. From there, we dove into the configuration and verification of IPv6 addressing and prefixes, a crucial skill that every network engineer needs in their toolbox. Next, we moved on to the 802.11 wireless, a standard that has become synonymous with wireless networking. We explored its principles and components, helping us understand the foundation of wireless communication. We wrapped up our discussion with a look at non-overlapping Wi-Fi channels and the importance of encryption in maintaining network security. Remember, understanding these concepts doesn't just make you knowledgeable, it makes you adaptable in a fast-evolving tech landscape. With a solid understanding of these concepts, you are well on your way to becoming a proficient network engineer.